All right, YouTubers. So here we go. And what we're going to be discussing today is this issue with analog signals, how the Arduino handle them. Let's start by a physical property. This is a physical property you want to measure. Let's say temperature. To measure temperature, you need a sensor. Let's say you have a sensor. There's a sensor that measure temperature. The question is, what's the output of that sensor? How that sensor will determine the change in temperature? There could be many things out there, like for example, might be a digital signal coming out. A digital signal. So, like for example, if the temperature here is 90 degrees, you see a 90-degree here. All right. Um, Usually, that's not the case when you are into Arduino business. So what you really have is that if you want to measure temperature, something change in the sensor and probably maybe the resistance value or maybe a voltage. So something that the sensor is measuring is causing probably the resistance of the sensor chain according to the temperature might be linear, might be not linear, or the voltage change. So in most cases, when you are dealing with Arduino, you have these two cases that to deal with. Like for example, let's say that you have a thermistor. A thermistor basically, you remember, looks something like this, in where the resistance value will change. This is ohms, will change according to temperature. I'm talking about thermistor. A typical curve of a thermistor looks like this. So as the temperature increases, let's say here 150 C, you have a very low resistance. Let's say that this value here is about 1 kilo ohms. See? Now, at the room temperature, let's say 25 degrees C, that value is typical about 10 kilo ohms. As the temperature even go down, then the resistance value can be very high. Let's say for the sake of the argument that when it's 0 degree here, you have about, no, I don't know, like 100K. Thermistor has a very typical, uh, you know, curve like this. What I'm saying is if temperature change, something change in the sensor. And if it's resistance value what is changed, what you have to do is put that into a voltage divider like this. In this voltage divider, this resistance value is the one that I'm talking that will change, and this you will adjust this to say 5 volts because we are talking about Arduino, and this is a voltage divider in where you put the resistance or the sensor that is changing temperature. You put it, you set up according to this. So now this is the output of the sensor, and that's the analog output that will go into the Arduino. And let's say the Arduino that you're using, Arduino Uno has some input for those signals, for those analog signals that will go like this. 1, 2, 3, 4, 5, 6, and this will connect here. And that's it. So now, if the temperature change here, you will have a corresponding signal going out. That's perfect. So what we need to do is whatever voltage will come out here, and that voltage out is very easy to calculate because that voltage out will be the voltage that we are using in the Arduino, which is typical 5 volts, multiplied by this resistance value, whatever is the resistance value, that will change. Let's call that RT, the T for thermistor, divided by the resistance R1 here, whatever value it is, plus RT. Now, careful here on this calculation. Remember, RT and R1 must have the same units. So let's say that for this case, it's very often that the type of thermistor that we use is called a 10K thermistor. That means that in most cases our voltage divider will look like this. This is ground, this is what is changing, and this resistance value here we call it 10K, and this is connected to the 5 volts, and this is V out, voltage out, that will go into the Arduino. So if you do that, then that V out is basically 5 volts times the resistance value here, the one that change according to temperature, divided by 10K plus RT. So if RT is basically has to be in units, like for example here, let's go to the curve. If you are 25 degrees, that resistance value will be around 10K. So what will be the voltage out at 25 degrees C? What we have is that the resistance value RT is equal 10K. So what will be B out? B out then will be 5 by RT, which is 10K. Check this. I'm not saying 10,000 because everything will be in with the K unit. So that will be 10K plus 10K. See, same unit. So this end up being that B out is equal 5. I can cancel the K, so that will be 10 over 10 plus 10, that's 20. So meaning that V out is basically 2.5 volts. So that's the output. So that's actually what you're gonna get when the when this is set at 25 degrees. This the thermistor, the V out. Let me. This is going to out. So let me put right here. Oops. Let me put right this right V out. That is going, let's say, to this analog input A0. With that said, let me close this. With that says, basically, the idea is now that voltage need to be converted to basically voltage is converted to ADC, analog to digital converter, and this is done within the Arduino. The Arduino Uno that we are using, it do the conversion like this. For example, 0 is 0 ADC, and voltage and the value here, maximum value is 5. 5 in the Arduino is 1023. So with that said, basically any value here of voltage out will be converted accordingly to another value here that we're going to call ADC, whatever value is there. So any voltage that come along will be converted then to accordingly to a value on the ADC side. So I definitely can make you can use, like for example, interpolation, that if you know voltage out, you will calculate easily what's the value of ADC that is going to be read by the Arduino. However, more than that is the fact that when you are using ADC, you lose the units. Like for example, see the temperature you're reading is centigrade or Fahrenheit, you totally lost the unit. You had it. You want to recover those units back to know precisely what you're working with. So if that's the case, oops, sorry for this. If that's the case that you are losing the units, you want to recover those units back. That's what's called calibration. We need to do calibration, and calibration is basically done between, for example, between the ADC, what is the reading on the ADC versus temperature again. And this is just an example. Let's say that that analog signal from the sensor is linear versus whatever you are reading here on your sensor. So meaning that, and I have to say this with very, with caution, because actually you can see that temperature and resistance value is not linear. Maybe it's linear within some small region, like for example those region, I call it, they are linear maybe, but it's not the whole range of, of temperature reading. So let's, for the time being, let's say that is linear, so that I can say that when the ADC, when the temperature here, for example, I have a reading of, let's say, let's put a number, any number here, like let's say 0. So the temperature is minus, I don't know, let's say, I'm saying, putting numbers. I'm not saying anything at this point. It's just a more like to understand where we're going. When the ADC reads 0, let's say that the temperature is minus 20, but that is degrees C. Now, when the temperature is 5 degrees, I mean, when the ADC, sorry, the ADC, let's say that is 700. Remember, the ADC can go from 0 to 1023. I don't know, the temperature is 100 degrees. I'm making the numbers. I'm not saying that that's the way it is, but the idea is, now when you have something like this, it means that, assuming that the temperature and the ADC are linear, then any ADC that comes along here, I will be able to convert that to temperature. And that's it. How we'll do that? Very easy. Use interpolation. Like, for example, interpolation here will be ADC, which is a number that you know, minus 0 over 700 minus 0 equal T minus, careful here, minus 20. You see, minus minus over 100 minus minus 20. Careful there. So the idea is to put our equation in terms of T. So that will be ADC over 700 equal T plus 20. 100 minus minus as plus is 120. This is an example. So the idea is to put everything in terms of T. So that will be, let's rewrite the whole thing like this, so make life easier. Equal ADC over 700. So now we got T plus 20 equal ADC over 700 multiplied by 120. Multiply 120 by both sides. Let's make it here so everybody knows what I'm doing. So this cancel with this one, and eventually you got that, and basically T, temperature, degrees C, equal ADC multiply by 120, the whole thing divided by 700, and then we subtract 20. You see, now we recover back the unit based on our value of ADC. Whatever value is of ADC, you are reading. Remember that the value of ADC will always be between these two values on the Arduino Uno, because the Arduino Uno have a conversion of 10, I think it's 10 bits, and that ADC conversion will add up to about a maximum of 1023. So whatever signal comes along from the analog, from B out, remember that B out in essence will be a value of 0 less than 5 volts, so, or equal to 5 volts. So this is the corresponding ADC of the conversion that is coming. And now B out will change according to what? Well, according to the temperature here. So that's one way to see it. So in other words, the summary of all this is come from here. If you have a temperature or a sensor that measures temperature and you measure resistance, the sensor will change resistance according to temperature. Is what you have to do is something like this, a voltage divider. So you put together a voltage divider like this, and that will do the trick very easily. And when you have that voltage divider in an Arduino, let's say that this is Arduino Uno, which is the analog conversion is based on 10 bits, then what you will eventually have is a table that looks like this, and the idea is to do or to recover the calibration, which you only care about the ADC value versus the actual temperature that is being read by the sensor. Like for example, if I see a 0 ADC and the temperature is minus 20, but that's okay, that's perfect. That's the temperature that is reading at 0. When I see it in the Arduino 0, it means minus 20. And when I see 700, I see a 100 on the other side. So in other words, you put the sensor in 100 in water that is boiling basically, right? So that's the main point here. And then from this table, which is called for calibration, this is what I call calibration, so that you recover back the units from the ADC. You do that and you end up with this equation. Whatever value of ADC I put into this equation, eventually this equation will resolve for temperature, the actual temperature. And when you have actual temperature, then you can do many decisions based on that temperature. For example, if it's too hot, you will send a message saying temperature is too high, shut the equipment down. Or if the temperature is okay, it's within the range. This is like in a car. If the temperature is too hot, you want to be sure, you want to check the engine, what's going on, why it's hot, and so then the nice thing is that you don't have like a light bulb saying, hey, it's hot. Now you know what hot mean, because you have the actual temperature of that in the engine, right? Just that's an example within a car. The important thing is that in this case I said clearly that you have a physical measurement you want to do, and that you have a sensor, and that sensor, the output of the sensor is a resistance value. So in other words, if the temperature change, the sensor measure it, and the output of that sensor is that a change in resistance value. If that's the case, you end up then using a voltage divider to convert that into voltage, which we call V out, and that voltage divider is set in such a way that the voltage is limited between 0 and 5 volts, because that limitation comes from the Arduino. But the nice thing is that if the temperature change, the sensor measures resistance through this voltage divider, then you get V out that is going to the analog signal A0 or whatever. Like for example, you are measuring many temperatures from an equipment, then the idea is that you have like for example as shown here, you have other pins that you can use for your measurements. Now that's perfect. So how about if I have temperature, a sensor, but the output of the sensor is already voltage? The nice thing is that the Arduino has been with us, I don't know, many years. I don't know, I think it go back to 2000 or so, if I remember right. So there are many sensors out there that are tailored that the output will be a voltage between 0, let me fix this, and 5. So if that's the case, if the voltage is between 0 and 5, that's perfect. You don't need a voltage divider in this case, because the output of the sensor is already in voltage. And there are many sensors out there that will do that. So I just want to be sure that you understand this type of sensor, that there's two kind basically. One, that the output is, or the change to the physical property you are trying to measure is a resistance value. Those need a voltage divider to be able to accommodate them into the Arduino. Now on the other hand, if the sensor already produce voltage, this is perfect, you are done. Because basically the way to work on those type of sensors is like, for example, I have a sensor here, Those type of sensor usually have three legs. One leg here, and another leg here. This leg, let's say that this is 1, 2, and 3. Leg 3 typically will go to ground, and leg 1 will go to 5 volts to power the electronics that is here. And its 2 is V out. And that's it. So, like for example, let's say that this is temperature, and here's the sensor. So you stick the sensor in the solution that you want to measure, the temperature, and basically V out will be a, a voltage corresponding to this temperature. This type of equipment tend to be linear, and those are great. What that mean, being said that they are linear? It means that the voltage out, let's say this is temperature, as the temp, maybe I'm writing this down, it could be either way. Like for example, it could be like this, like as the temperature, let's say from 0 to 100. So the temperature, the voltage out will go from some value here like this in a linear fashion. So you have a curve like this, straight line, and perhaps that will go like here. So as the temperature go down to some value, uh, and this is V out. Obviously, this meaning that uh, the voltage out will never be, like for example here, the voltage is less than or less than this voltage here. Let's say here, that's the maximum 5 volts. So this sensor will not be able to, if the sensor is for 100 degree, this and 100 degree meaning 5 volt, this will not happen. I mean, this way is not going to happen because the sensor will not be able to measure higher temperature than 100. On the other hand, it will not be able to measure temperature below 0 degrees because that will be negative value for V out, and V out cannot be negative. So V out definitely will be maintained within 0 and 5 volts because that's what the Arduino require. There are other sensor. I mean, it's again, it depends on the sensor. There are other sensors that might do like this. In that case, that sensor, let's see, this is temperature again. This is temperature. I thought about that. Let's see. Yeah, temperature, and let's see that this is voltage. Voltage. So when the voltage, don't like that curve. Let's do. Let me see. Let me do between 0 and 5 volt. Let me do the voltage in this scale so that looks better, and that's its temperature. Make life easier. There we go. See, in other words, the way I put then the graph make more sense if I do temperature versus voltage. Never mind. I mean, it's a linear curve. So the important thing here is that I can measure negative value of temperature. Let's say this is -20, and this is 150. So let's see. Let me do this way, and this is actually 150 here because it get to the maximum of the sensor. When the output of the sensor is 5 volt, it means that the temperature is at 150 degrees C, and when the voltage is 0 volt, it means that the temperature is -20. So this is basically an output that you can get from a sensor that is not using the concept of voltage divider because they has the required electronic here to make the output pretty much linear with temperature, which they are great. They are the one that you really need. Thermistor are the simple one, but their corresponding curve is not that linear, and they tend to be a little bit more fussy about it. Anyway, so what we're gonna do at the end of this discussion is we're gonna look for a thermistor, not a thermistor, but a temperature sensor that the output be a voltage. We're gonna connect it to the Arduino. Let's say this. Let's say this. Let's say this. We have the Arduino here. Let's do this. We're gonna connect a sensor, a temperature sensor, um, and this is the output of the sensor. We're gonna connect that to A0, and one of the leg of the sensor will be to 5 volts, and the other leg will be to ground, like this. And so whatever temperature you read here, you will subject this sensor to different temperature, and we're gonna collect what is the ADC. So in other words, we're gonna change temperature. Temperature will be on our X side, and the ADC will be on the right side. So in other words, temperature, if I have a temperature here, a value, I'm going to have an ADC corresponding ADC here. I change temperature here, I have another ADC. So we're going to, get this table. And with that table, the idea is to do calibration. Calibration. Remember, how are we going to do calibration? And here is the part that may confuse you. Typically, on calibration, ADC will be will be located on the x-axis, and temperature will be in the y-axis. That's all what I'm gonna say. You can have the table like this, or if you prefer to avoid problem, let's say with Excel and confusion, maybe you want to have the table better like this: ADC, analog to digital converted, and temperature. So you change the temperature, and then you get the corresponding ADC value. I believe that this, in doing like this, will be more aligned eventually to this, because what you're gonna get at the end, remember, the ADC is a value between 0 and 1023, which is the maximum. And now what's gonna happen is, let's say that 1023 is the maximum temperature you can get, 150, just to say the least, a number, and the minimum is somewhere here when it's 0. So you have a curve like this, or like a straight line. And that equation, the equation that come out from here, is the equation that you want to put into Arduino. So that in the Arduino, temperature will be the slope of this equation multiplied by the ADC plus the intercept, whatever value come out from the intercept. So this equation is the one that you need in your Arduino, and now in that way you recover the unit, which in this case probably is going to be degrees centigrades. Now, summary. What's the summary? You want to measure a physical property, whatever it is. Let's say temperature. You need a sensor. The question is, what is the output of the sensor? You need to understand that. If you don't understand what's the output, you are in difficult waters. What is the output of the sensor? Mostly could be a resistance value. If it's a resistance value, if R change in the sensor according to temperature, then you need to install a voltage divider. That's it. And then finally you get V out. But if the sensor output is already voltage, careful here. If the sensor out is voltage, the only question you need to ask yourself is what type of voltage? Because it has to be the voltage out from the sensor. If you want to use this in the Arduino, it has to be between 0 and 5, which in most cases it is if you are buying a sensor for the Arduino that measure like the output is voltage, because there's many sensor out there that's what's gonna do. There are other equipment, other computers that don't use 0 to 5 volt, use something else. Like other computer can use from, I don't know, they are weird. They can go to I don't know, -10, 2 plus 10 volts. Other can use other voltage range from 0 uh, to 100 millivolts. So these are not good for Arduino. Obviously, these are not good for Arduino either. Uh, you want to look for something like this. That's for the Arduino. Arduino requires on the analog that they use in the analog signals to be a voltage of 0 to 5. Could not be higher than 5, could not be less than 0 because you can damage the Arduino's analog pins. So, going back to what we're going to do, we're gonna install a sensor that the output is voltage out. We don't gonna use a voltage divider because the sensor that we are planning to use will produce a voltage out, which is very ideal to connect right away to a signal within the Arduino. In this case, to the analog to pin A0. We're gonna read that pin, and based on that pin, we're gonna write. You can drive LEDs, for example. If the temperature is too high, you want to perhaps drive a red LED. If the temperature is right, maybe you want to drive a green LED, and so forth. So there are many things that you can do when you have an analog signal, the range of analog signal being read through an Arduino, which in this case is going to be Arduino Uno. With that said, let's do an example. I'm going to be using Tinkercad for this example, and let's work out something good with it. See you in a moment. Bye. All right, so here we are in Tinkercad. So let's build this very quickly so everybody understand how we're gonna do with analog signals. So let's say let's go all here, and let's start to bring what we need. We need a temperature sensor, and we can put here, like for example, temp. Let's see what show up. Temp sensor TM36. There we go. We're gonna put that there somehow. Now, that's the sensor that we're gonna be using for measuring temperature, because that will be our analog signal. If you don't understand this, one thing that you can quickly do to understand how this sensor will work is go here and let's add let's see, a meter. Let's see how quickly I can get a meter here. Multimeter right here. We put it here somewhere. Now we also need, like for example, let's use a power supply. Let's see, power supply. That will do. Let's put a power supply so we understand what we're doing. So we need those three instruments basically just to test how this works. Now, first of all, this guy needs power. So you need to check that this is 5 volt. Perfect. So very quickly we go here. We power this guy. Now this one is for ground. So we get the ground here. I'm gonna do this very quickly. So the idea is that you quickly understand how this TMP works. And now we want to measure the voltage out of this guy. Now we need this also need to go to ground. Good enough there. So this is V out. Let's put this red so we understand this circuit. This is black, and this is black as well. And let's say this is a signal. Let's change that to blue. That will do. So now this guy, when you touch it, has to be in voltage because it's going to be measured in voltage. Now here's the trick. This guy will change temperature. It's a simulation. So meaning that when I run this start simulation, see, right now, let's check where it is. As you can see, right now it's at 25 degrees. It tells you what the temperature is, but it also tells you what's the voltage that is producing, almost 1 volt. So if you move this back, so you can see that at minus 40 is reading 99.9 millivolts. Okay, but then if I go to the maximum, it's reading as about 1.75. So the question is how linear it is. We will find out that at a later time. But the important thing is that if the temperature change, this guy is producing a millivolts, which is within the range of the Arduino. The Arduino wants something that be between 0 to 5 volts, and this is perfect because it's right between 0 and 5. This is called TMP36. Again, this is perfect. That's all what we want to know. That yes, if the temperature change, there is a change reflected by the sensor directly here in voltage. As you can see, about this temperature is about, let's see, we get it very big here so you can see it. It's about 125. I got 1.75. If I drop this to minus 4, it's 99.9. So as the temperature increase, the voltage increase. All right. So what we need to do is to install an Arduino to start to read this signal because it's perfect. It's what we want. That's perfect. Now, let's stop the simulation. Let's delete what we don't need at this point. I don't need anything of this. I'm gonna leave the sensor there. But to make this more, more easy to deal with, let me get an Arduino here so that I can start to make this better. An Arduino Uno. Let's see, here is gonna bring an Arduino Uno. Now, here in the Arduino, as you can see, are the analog pins that we're gonna be using. Now, let's bring a breadboard. Make life easier. Let's see if I can see one here. I don't see it. You can always check here on all, and you can always, look for them. And for example, small breadboard. This will look good. Now here's the story. This sensor need 5 volt and need to be in ground as well. Let's say that I put the sensor here, anywhere. Actually, let's put it here, a little bit higher here. Now remember, this is positive. So basically, one thing that you could do is put a connection between this pin and the positive pin here, and now from the 5 volt here, do a connection up to anywhere here, meaning that that line is red. That will power eventually the Arduino. Let's put that red as well. Now the ground. How about the ground? For the ground, I need a pin that will connect a cable connector that from here to here. Now that one require to be black just for understanding. Here's the ground. It's very easy to come with a cable from here and put it somewhere here. There we go. So we have both the positive and the ground for the TMP. The cable at the center is the one that need to come right to whatever of this pin you want to use. Let's say that we're going to use A0. So now the voltage is going to be the voltage out, as you can see here, from the sensor is going to be read by the Arduino. That's what we want. Basically, we are ready to have a small code now written so that we can see the temperature. For this, we're going to use, for example, let's program very quickly the Arduino. This is all what you need. The sensor and the Arduino. Now, the small code that we're going to write is something that looks like this. Text. We're going to continue here. All that is there as a reminder of how to program the Arduino. At this point, I'm not using anything on the voice setup. I'm not programming anything yet here. So that can be left like that. Now, in the void loop, I definitely want to read the Arduino. So let's delete all this for 1 second. Everything that is there. And let's start to write the code. The first thing that we want is to use the serial monitor. If we want to use the serial monitor, then we need to add something here to let them the Arduino know that we're going to be using the serial monitor. For that, let's say serial begin. We're going to write this. Whoops, let me get this right. This is not right. Serial begin, and we're going to put the speed of 9600 baud rate. That will do. So we have set our serial monitor. Now inside here in the loop, we're going to start to read this signal. Let's say that we want to assign that. It's good practice to assign that to a variable. And that variable, let's say, is going to be an integer, because the analog conversion is an integer value between 0 and 1023. So we're going to call that, let's call it ADC. Now, careful here. ADC might be special word within the Arduino. I'm going to call it ADC1, so that that value will be, that variable will be used to save the value that I get from the conversion. And now for the conversion, it's going to be ADC1 equal read, analog read, sorry for that, it's going to be analog. I have to be careful with the spelling here and the capital letter, analog read, and that's going to be A0. Now I'm reading the value. The value is going to be saved on this variable, and you will see why we're going to save it there. It's a lot easier. Now if you want to see what is the value, eventually we want to now write it into the serial monitor, which is kind of nice now that it's activated by this instruction here. So what we want to do next is say something like a serial print. Now here we go. LN, we want carriage return on the serial print, so we put the LN. And now we got right ADC1, and then we're going to delay a little bit the next reading, so it's going to be delay, let's say, by 2 seconds, so that's 2000 milliseconds. Be sure you put the semicolons at the end. So basically, let's go through this code once more. So I set a variable that is called ADC1 for saving the value that I'm reading directly from the analog pin. And then in the void loop is the thing that I want to do forever. In this case, I'm reading the analog read A0. If the analog is A1, for example, you change to A1, A2, A3, A4, up to A5. Now, serial print LN, it means that it's going to print and then push a carriage return. So it's going to be next line, next line, next line. We're going to delay 2 seconds basically here, and this N will go back here to read a value and print it. But remember, we are printing here is ADC, not temperature. And that's the part that I was telling you before, that you want to recover via the calibration the actual temperature back. So let's say start simulation, and we're going to open the serial monitor to see what is printing. You see 153. That doesn't mean anything. That's kind of weird. Now step here, and let's get this big so we know what's going on. 153. That 153 is equivalent to 25 degrees C. That's the ADC that I was talking. For calibration, like for example, if I move this to -40, you get a 20. You see? If I move this to 125, so the temperature is very hot, 125, I get 358. So what we're gonna do is, let's say if I try to do a calibration with only 2 points, I might miss the fact that it's not linear. So I need more than 2 points to ensure that yes, the calibration is as linear as it can be from the range of temperature that this TMP can measure. Like for example, from -40 to maximum temperature, which in this case will be 125. when I move to 125, you can see that the range of the instrument in ADC is from 20 to 358. How about if I put it somewhere here? Well, how about 105? If this is a linear curve, then you will have more, I mean, this 319 should be within the line of the calibration, hopefully, because we are saying again, if this instrument is linear, we should have a linear result. Now, how are we going to do this? Very simple. This is the part that is done by hand. So what we're going to be doing now, I have already Excel here. We're going to change the temperature, walk the temperature up and get what is the temperature I'm using and what is the corresponding ADC value. Like for example, here is minus 40 degrees C. That corresponds to a value of around the ADC, around 20 on the ADC. Now we go back here again to this guy, and let's say that we want to jump to minus 30. We stay there. Minus 30 corresponds to 43, so we go back to Excel. We put here minus 30, and we put the corresponding value on the ADC. That's 43. Notice that I'm plotting this way because the ADC is in the X axle and the temperature will be on the Y axis. All right, so be careful with that. Now, if I come back here, I can try to expedite this faster. Let's say that I move to 0. If it's linear, it will show up. Right, 0. What's the value of the ADC? 104. So we go back to my Excel and let's say that this is 0 degrees centigrade and this is 104. All right, so let's go back again to and let's say that 0, let's say 20 plus. Ooh, 20. I want a 20 here. It's a little bit could be any temperature. I mean, I just want to be 20, but if it's hard, could be any. It doesn't want to step, well, let's say 22, because that's where it's a little bit hard to step. My mouse is not the best of the world. So 22 equal to 147. So that's the one that I want to use. So in this case, I think that 127, I don't know. And this is 22 degrees. If it's wrong, I can go back and check again to see what was 147. Sorry, 147. You have to use the right value. You cannot use anything. You have to use the right value. So let's see. Let's go back here. That's 22. 22 with 147. 22 and 147. So let's say, I don't know, whatever is stop. Let's say stop here at 50. Let's see if I can hit the 50. Oops, hard. Oh, whatever, 54. It doesn't matter. It would change the ADC accordingly. So 54 is 213. All right, so we go back here and let's hit, I don't know, stop at 87. 87 is 282. And as you can see, you don't have to be precisely the number you want here on the temperature. You might want some particular value, but it's not happen. The important thing is that that temperature is converted to a given value during the conversion to ADC. And let's get another one. Let's see. Let's get I don't know. Let's get to the final one. 125. 125 is 358. 125 is 358. Bingo. So we have, more than, actually, if this is linear with only these 2 points, I will be able to get my equation that I want. But I put all the numbers, as you can see, from the range of temperature from minus 40 to 125 because I want to be sure that it's linear. All right, let's do that. Let's make now a graph or a plot in where temperature will be on the y side and and the ADC will be on the x side. So insert, we go here, we go here, and let's use this. Perfect. One thing that we want to be sure is that let me reduce this a little bit. That's way too much. We want to be sure, as you can see, uh, that is plotting what is supposed to be plotting, that the ADC is on this axis and in this axis is temperature, because otherwise we are in, it's not going to work. We are in a problem. So as you can see, the 20 is somewhere here, 20 here on this line, and that's correspond to the -40, which is perfect. Now, as you can see, the points are pretty much in a straight line. That's even better. Just to demonstrate that this is a linear correlation between temperature and ADC, let's add a trend line. And let's have the displays of the equation. This equation is the one that we want, because basically here we have the slope and here we have the intercept. This is perfect. This is what we need. In this case, the y is going to be temperature and the x is going to be ADC. So you are pretty much, this is the curve that we need for calibration so that we recover back the unit. Again, this is because it's linear. And I can definitely use this equation from -40 to 125, and the output will correspond to perfectly to temperature, to the right temperature that we want. Like for example, if the output is 250 on the ADC, that would be converted to a temperature between 80 and 60 degrees, somewhere here, right? Around the 250 value. So any value that is maintained between, let's say, 20 here and somewhere above, a little bit below 400, is within the linear range of the instrument. Excellent. So again, what we need is this. Let's copy this. Copy. And let's go back again here. As you can see, we are reading ADC. You don't like ADC. ADC, it doesn't mean anything. You have to recover back the engineering units. Let's recover back the engineering unit now that we have done the calibration. How are we going to do that? Very simple. Let's stop the simulation for 1 second. Now, here, I'm reading the ADC. How about if that value is converted to temperature? I'm paste the equation. Now, a little bit changing the variable here. This is going to be called temperature, or temp. And x, what is x? X is the ADC value, but in this case, it's going to be time ADC. The way I call it here is called ADC. Be careful here, it has to be cap letter ADC1 because I call the variable ADC1. See? Perfect. Now, temp is a floating number. I want decimal on it. So let's say here as a variable, I'm going to set that that's going to be a float. It's going to be a float, so that includes decimal numbers, temp. Again, cap. If you are using cap, it is cap. It is cap sensitive, so you want to be careful here. Want to be careful. So it's temp because the name here is temp. Now, the variable temp will be the equivalent with engineering units. So whatever is being read by the ADC1 is going to be converted by this equation back to what we want, which is temperature. Now, at the time of printing, let's fix this. Let's say that I'm going to be printing first. It's going to be printed the ADC value. We wanted this to look good. So let's fix the printing process better. Let's say serial print, and we're going to print here a little text. Text need to be on quote. Let's say that that text is going to be ADC value equal, we close the quote and we close the parenthesis and semicolon, and now we put what this line will be perfect there, will be okay, because after this is printed, you're gonna print the ADC. Now we want to eliminate the LN, so you are still within one line. So this is gonna be a long line saying something like ADC value equal, then it print the real value. But after that, we want some space, so let's write here serial print, again without the ln, and let's put some space so this looks good. For space is basically some quote, some space, close it, and again semicolon. And now we want to print the temperature. For this, maybe I can put here some space there. Let's write the word temp here, or in this way, temp. Even better, temp equal. Now that will give some space. That's too much space after temp. You don't want that much space. Maybe one. And the same here, maybe one after that. And what's going to happen is that this value is going to be printed. There's going to be some space. It's going to write the word temp, but now we want the value after that. So the value will be serial print. Now, this is the last print for the line. Now you want to put the LN, meaning the carriage return, and the name of the variable, which is this case is cap letter temp. We close and semicolon, and then we delay 2 seconds and we go back again. After this, we go back, and this is going to be repeated forever. So that's the idea. Again, where this equation come from? It comes from the fact that we complete a calibration manually. When we have the calibration, we come out with a curve fitting, and if it's linear, then we end up with this straight line, and this straight line end up with this equation. This is the slope of the equation, and this is the intercept. We copy that equation. We only have to remember that the y here is temperature and the x is ADC value here. And with that, we come back here. As you can see, I'm ready to see now both at the same time, the ADC and the equivalent value in terms of temperature. So let's clear this data and let's run this again. Start simulation. If I miss something, it's gonna show up right there. It's saying, it's a problem here, and the problem is because I forgot to add semicolon here, and that's what it's saying right here. So start simulation again, and let's open the serial monitor. As you can see, it's telling me the ADC value equivalent to 24.44, which is basically the 25 degrees plus minus 0.5 degrees, which is basically the error of the measurement, but it looked good. Now let's go here to minus 40. The minus 40 is giving the 20, and the minus 40.64, no bad, pretty much right with plus minus 1 degree or less than that. Now how about the 125? 125, perfect. It's 124.75, and again the 358, which was part of the calibration. So what we have done through this process is to recover back the signal or the unit that this sensor is measuring in centigrade. That's as simple as it can be. Now, the nice thing is when you recover the unit back, then you can do very nice comparison. Like for example, if temperature is too high, you want to do something. If temperature is too low, you want to do something else. Blah 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 blah. And let me do that very quickly here. Let me stop the simulation, and let's go back here. I'm reading temperature right there, right? Let's say that if temperature is too high, I want to have a comment, something like a comment, like temperature is too high or temperature is too low. Actually, let me put it somewhere here. Let's say after this temp, let's remove the ln, because the same line I want to have everything. Temperature, and now we're gonna print this. But it's gonna be an if process. If temperature is higher than a given value, let's say if temp greater or equal, I don't know, what would be greater than equal? I don't know, a good value to say that the temperature is too high, of 100. If temperature is above that, then I want the following to happen. I want to have a comment printed. So serial, let's open first here one of these, and let's say serial print. And since this is going to be the last one, we're going to set serial print ln, and that's the comment. And the comment LLN carries it. There we go. And this is the comment. So we're going to write here temperature temp, or let's see, temp too high. Whatever. You have to do something, right? You do it. But it's going to send you something based on that the temperature is too high. Perfect. Now, we close here and we said, if temperature greater than 100, how about else? Meaning, if the temperature is not above 100, we want to do something else. So we open here another one and we said, all right, let's copy this because it's basically the same. You're going to copy this, but this is what you're going to set before I'm only copy. And else, we write here, if temp less than the 70, this is taking 100. If temp actually higher, let's say it's temp higher than 70. If this goes like this through this process, it's going to check this. It's not, if it's not above 100, this will not be printed. It will jump to this one. Now, if temperature greater than 70 or equal, so let's call that will be kind of a, I will say, so if temperature greater than 70, we apply the same we did here. We're going to print this. So we're going to open a bracket, and within this bracket, we're going to put, now maybe the temperature, if the temperature is above 70 but below 100, then if the temperature is normal, normal is a normal temperature, normal temp, and so we close that with a bracket. That's it. Now, what's going to happen if the temperature is below, let's say that the temperature now is not above 100, it's not above 70. In that case, let's say else, we're going to check that last condition, else, and we're going to say if temp less than 70, we're going to close here, we open again this, and we're going to set there, we are almost done, is that temperature temp below, oops, let's put this cap so it looks good, temp below normal. All right, so now this with this, let's see, and the last one that is to close the loop, the void loop. So again, going back here, the first thing that we do in the loop is read the analog, save the value on ADC1. using this equation, which is called calibration, we say the value in temp. Now, here in the first line, we print the ADC value, no carriage return. Then we put the value of the ADC, no carriage return. Then we print the word temp. Then we put the variable, no carriage return there, because the one that will carry the carriage return is the one that has ln, which is the final comment on the one line here. So temperature too high if it's above 100. If the temperature is between 170, will print normal temperature. If the temperature is below 70, it will print temperature below normal, and that will do. And this is the delay to wait for 2 seconds and then repeat the cycle again. And let's see how this looks like. Let's see. Let's check that the semicolon is where they should be. That's one thing. You look careful. The if don't have semicolon because they are expecting this to be completed with this line. The else doesn't have that. So how you read this? If temperature is greater or higher than 100, yes, we get inside here. The else, it will not matter because it's already went through this one. So else it would not do it, and this one would not be done either. So meaning that it will return back to see where the temperature is. So this is how it will work. We're gonna clear this. Let's see how many mistakes we have. There's always a possibility that I have missed something or misspelled something, and we start. Let's see what we'll do. There we go. Let's see. Expected at the end of input. There's a problem here somewhere, and let's see whether I have more than I should have or not. All right, which one it is? Oh, expecting one closing. Let's see. Sometime you see there's a problem here. Open. This one hit the wrong key. This one should be closed. There we go. It's hard to see. Open, close, open, close, open, close, and the last one, which is this one, close. Which one? Close this one that is open. Perfect. Now that should do. Start simulation. Open the serial. Excellent. Temperature below normal. I don't like the fact that is this all together. Too tight here to see what's going on. So let's fix it. Stop simulation again. And the problem is here. The comments are too tight to the number. So let's give a little bit of space here, and that will fix the problem so that this line will be easy to read. So let's clear again, and now that the bugs were corrected, start simulation. Excellent. So let's stop. Well, actually, let's keep going. Like for example, temperature 153, the ADC value is 153, the conversion is to 2444, temperature below normal. Obviously, it's too cold. So if I move this, like sample to temperature now is too high. So it's giving you the comment because the temperature definitely is too high. It shouldn't be above 100. Now, if I put the temperature somewhere here on the 90, temperature is normal. So you can see what the else will do. If temperature higher than this, yes or not. If not, else. If temperature higher than 70, no. Keep asking until you finally find that the temperature is below 70, and then it's the last comment, and you go back again. So this is the nice thing that you can do when you recover the unit of the sensor, because you can work at the actual unit with the actual unit of the sensor, make life a lot easier to do many things. Like for example, if temperature too high, now I can turn a light here, a red light. You can connect all this concept to LEDs for feedback of what it is. Like for example, right now our comment within the computer and the serial monitor, but you can definitely build here some LED that will do the trick. All right, so I hope this get the mystery about how to work with analog signal, how to get back the unit that you want, and what you can do when you are within the, with the correct unit for your sensors, that you can do like interlocks to do certain thing. If something happen, I do this. So, and this is basically how interlocks will work. Like for example, temperature too high, shut the engine. That can be done. Something is happening. Let's do this. Let's do that. Whatever, or according to some programmed scheme to do or to handle the abnormal situation. Like for example, temperature too high, you can do many steps that you want to do to ensure that the equipment is shut down properly. You can certainly do that. But again, everything starts with this concept: a sensor that measure a physical property, in this case like temperature, that sensor, the output is voltage. Nice, because then the Arduino don't need a voltage divider. That go directly into, like for example here, the analog signal A0. Then you read that signal, and that signal is being, then eventually you do calibration, so you get again the proper equation for that, which is this one. And it's interesting because this is linear. This cover a big range. Thermistor are harder than that. Thermistor might have might end up having many region, which are linear, but many region together. You know what I'm saying? Like you might have like three linear curve to describe the full range of the thermistor. So you have to be, you want to be careful at what range you are to use the proper equation, which is linear. Again, for a linear equation, you only need the slope and the intercept, and so forth. So, but again, this kind of a sensor, the TMP, being linear, will produce this kind of line, and it's kind of easy to, do the calibration and end up with an equation like this. So when you go back, then you can have an instrument like this, reading temperature, but then providing you with proper comments to understand that yes, the temperature is 91, but it's still on the normal range. As the temperature, get to any other value, then the comment will change, because now the temperature is too high, whatever, So, like for example, let me get this, like 180, 118 is too high, 114, 113, because that's what the thing that we program. We program that to give us this type of message as the temperature was too high. If I get to about 100, 99, 98, now the temperature is back to normal. So, oh well, folks, that's basically it. I hope that you understand everything here. And any doubt, just hit a comment, and I would be glad to answer any questions. Again, thank you. Have a great day. Bye.